On a clear, dark night, far from the glow of city lights, one can gaze upwards and witness a truly breathtaking spectacle. This experience, known as stargazing, is profoundly different in areas untouched by light pollution. In these remote locations, the human eye can detect thousands of stars, and the sky reveals its true depth and complexity. A faint, luminous band stretches across the heavens, a celestial river of countless stars, so distant they blur into a gentle, milky haze. This band is the combined light of billions of stars, so far away that their individual points merge into a continuous glow. What we see is the galactic plane, the densest part of our galaxy, viewed edge-on from our position within it. This is our home, the Milky Way galaxy, seen from the inside out. The Milky Way is a barred spiral galaxy, a vast rotating disk of stars, gas and dust, with a central bulge and spiral arms extending outward. Our solar system is located about 27,000 light-years from the galactic centre, nestled within one of these spiral arms, the Orion Arm. For millennia, this was humanity's only view of the grand structure in which we live. Without telescopes or modern technology, ancient observers could only speculate about the true nature of this glowing band. They saw it as a continuous feature, not realizing it was composed of individual stars, nebulae, and interstellar dust. It is an intimate yet profoundly mysterious sight, a constant reminder of the sheer scale of the universe. The Milky Way contains an estimated 100 to 400 billion stars, and its mass is dominated not only by visible matter but also by dark matter, an invisible substance that exerts gravitational influence, shaping the galaxy's rotation and structure. To look at this band is to look into the dense, crowded plane of our own galaxy, a disk of stars, gas and dust that spans more than 100,000 light-years from edge to edge. The galactic plane is rich with molecular clouds, vast regions of cold gas and dust where new stars are born. These clouds are so thick in places that they obscure the light from stars behind them, creating the dark lanes and patches visible to the naked eye. We are but one small part of this immense cosmic city, peering out from our own stellar neighbourhood. Our solar system orbits the galactic centre at a speed of about 220 kilometres per second, completing one revolution every 230 million years, a journey known as a cosmic year. Ancient cultures across the globe were captivated by this celestial feature, weaving it into their mythologies and cosmologies. Without the benefit of scientific instruments, they interpreted the Milky Way through stories, seeing it as a river, a path, or a bridge connecting the heavens and the earth. To the ancient Greeks, it was Galaxias Kyklos, the Milky Circle, born from the spilled milk of the goddess Hera. This mythological explanation reflected their attempt to understand the origin of the galaxy, and the word galaxy itself is derived from the Greek Galaxias, meaning milky. This very myth gave us the word galaxy. The Greeks were among the first to record systematic observations of the night sky, laying the groundwork for later astronomical discoveries. In China, this same band of light was seen as the Silver River, a celestial barrier separating two mythic lovers, represented by the stars Vega and Altair. This story is celebrated in the Qixi festival, which marks the annual reunion of the lovers as the stars cross the sky. The San people of southern Africa saw it as the spine of the night, a structural backbone to the sky itself. Their stories reflect a deep connection to the cosmos, recognizing the Milky Way as both a physical and spiritual feature of the universe. The Lakota people of North America viewed it as the spirit path, a road taken by souls on their journey into the afterlife. This interpretation highlights the role of the Milky Way in guiding and connecting generations, both in life and in death. These stories reveal a deep, shared human need to make sense of the cosmos and our place within it. Across cultures, the Milky Way has served as a canvas for imagination, a source of wonder, and a symbol of the mysteries that lie beyond our world. What is truly fascinating is how different cultures interpreted not just the light, but the darkness within it. The dark patches are not empty space, but regions where dense clouds of interstellar dust block the light from stars behind them. These are known as dark nebulae, and they play a crucial role in the life cycle of stars. The Inca civilization, for instance, identified the dark patches within the Milky Way, vast clouds of interstellar dust that block the light from stars behind them, as celestial animals. These dark nebulae, such as the Coal Sack and the Great Rift, are now known to be stellar nurseries where gravity causes gas and dust to collapse and form new stars. They saw a great celestial llama, a fox, and a serpent hidden in these dark nebulae, turning the absence of light into a vibrant part of their celestial zoo. Modern astronomers study these regions using infrared and radio telescopes, which can penetrate the dust and reveal the processes of star formation within. This demonstrates a remarkable level of astronomical observation, recognizing that the river of stars was not a uniform band, but a complex tapestry of light and shadow, full of texture and depth. The interplay of bright star clusters, glowing nebulae, and dark dust clouds creates a dynamic, ever-changing landscape that astronomers continue to explore. These early interpretations were the first steps on a long journey of understanding the true nature of our galactic home. With the invention of the telescope in the 17th century, astronomers like Galileo Galilei were able to resolve the Milky Way into countless individual stars, forever changing our perception of the universe. From our vantage point on Earth, it is almost impossible to grasp the full structure of the Milky Way. We are embedded within the galactic disk, surrounded by stars and dust, with our view limited by the very material that makes up the galaxy itself. Imagine trying to draw a map of your entire city while never leaving your own house. You can see your street, perhaps a few neighbouring buildings, but the overall layout remains hidden. This analogy captures the challenge faced by astronomers attempting to map the Milky Way from within. This is the challenge that has faced astronomers for centuries. Only by combining observations across the electromagnetic spectrum, visible light, radio waves, infrared and even X-rays, have we begun to piece together the true structure of our galaxy. The beautiful hazy band that inspired so many myths is in reality a source of cosmic frustration, as its dense concentration of stars, gas and dust obscures our view of what lies beyond and at the very heart of the galaxy. The galactic centre, home to a supermassive black hole known as Sagittarius A*, is hidden from optical view by thick clouds of dust, but can be studied using radio and infrared telescopes. It is a beautiful curtain that we have only recently learned how to peek behind, revealing the true magnificent shape of our island universe. Through missions like the Gaia spacecraft, which maps the positions and motions of over 1 billion stars, and radio surveys that trace the spiral arms, we are finally beginning to understand the Milky Way's structure, history, and our place within this vast cosmic tapestry. For more than a millennium, humanity's understanding of the cosmos was shaped by the geocentric model, a vision of the universe meticulously described by the Greco-Roman astronomer Claudius Ptolemy in the 2nd century CE. According to Ptolemy's Almagest, the Earth was fixed, unmoving, and at the absolute centre of all celestial motion. This model, known as the Ptolemaic system, was not merely a scientific hypothesis. It was a comprehensive worldview, deeply woven into the fabric of medieval science, philosophy and theology. In this intricate system, The heavens were imagined as a series of nested, transparent spheres. Each sphere carried a celestial body: the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally the sphere of fixed stars. These spheres rotated in perfect circles, a motion believed to reflect the divine perfection of the heavens. The apparent wandering of the planets, or retrograde motion, was explained by introducing epicycles, smaller circles upon which the planets moved as they orbited Earth. The geocentric model was compelling because it matched everyday experience. We see the sun rise in the east and set in the west. The stars wheel overhead, and the ground beneath us feels solid and still. There was no observable parallax, the apparent shift in position of stars due to Earth's movement, so it seemed logical to assume the Earth was stationary. For centuries, this elegant but ultimately flawed model dominated intellectual thought. It was enshrined in the teachings of the Catholic Church and became the foundation for medieval universities. The Ptolemaic system was not just a scientific theory, it was a cosmological framework that shaped humanity's sense of purpose and place in the universe. Within this worldview, the Milky Way was interpreted as a mysterious, luminous band on the outermost sphere of fixed stars. Some ancient philosophers speculated it was the path of the gods, while others believed it was the result of the stars' collective light, blurred by the celestial sphere. This perspective was deeply comforting. It placed humanity at the centre of creation, suggesting a universe designed with us in mind, a cosmos where every celestial movement had meaning and purpose. But in the 16th century, this certainty was upended by a quiet revolution. Nicholas Copernicus, a Polish mathematician and astronomer, began to question the convoluted complexity of the Ptolemaic system. He noticed that the system's reliance on epicycles and deferents, circles upon circles, grew ever more complicated as astronomers tried to match theory with observation. In 1543, Copernicus published De Revolutionibus Orbium Coelestium, proposing a radical alternative, the heliocentric model. In this new system, the Sun, not the Earth, occupied the centre. The Earth and other planets revolved around the Sun in circular orbits, while the Moon orbited the Earth. This model elegantly explained the retrograde motion of planets as a natural consequence of Earth's own movement around the Sun. The Copernican model was a monumental paradigm shift. It challenged not only scientific orthodoxy, but also the philosophical and theological assumptions of the age. If the Earth was not the centre, what did that mean for humanity's place in the cosmos? The heliocentric theory demoted Earth to just one planet among many, orbiting an ordinary star. This was a profound blow to the anthropocentric worldview that had dominated for centuries. The new model was met with skepticism and resistance. Many scholars found it difficult to accept, not only because it contradicted scripture and tradition, but also because it seemed to defy common sense. If the Earth moved, why didn't we feel it? Why didn't the stars shift position as the Earth orbited the Sun? Copernicus's model implied a universe far larger than previously imagined. If the stars showed no parallax, they must be unimaginably distant. The Earth, once the stage for all cosmic drama, was now a tiny speck in a vast, indifferent expanse. This was the first great step toward a scientific understanding of our true place in the galaxy, a journey that would continue for centuries. The next leap came in the early 17th century with the invention of the telescope. Galileo Galilei, an Italian physicist and astronomer, was among the first to turn this new instrument skyward. His observations would provide the crucial evidence needed to support the Copernican model. Galileo's telescope, though primitive by modern standards, magnified the heavens tenfold. He observed the rugged surface of the Moon, the countless stars of the Milky Way, and the phases of Venus. Each discovery chipped away at the old geocentric worldview. Most strikingly, Galileo discovered 4 moons orbiting Jupiter, now known as the Galilean moons. This was direct evidence that not everything in the universe revolved around the Earth. Here was a miniature system, a planet with its own satellites echoing the structure of the Copernican cosmos. Galileo also observed that Venus exhibited a full set of phases, from crescent to gibbous to full, just like the Moon. This could only be explained if Venus orbited the Sun, not the Earth, further confirmation of the heliocentric model. When Galileo turned his telescope to the Milky Way, he saw that it was not a cloudy band, but a dense collection of countless stars. This revelation hinted at the true scale and complexity of our galaxy, suggesting that the universe was far vaster and more intricate than previously imagined. Galileo published his findings in Sidereus Nuncius, or Starry Messenger, in 1610. His observations provided powerful empirical support for the Copernican system, but they also brought him into conflict with religious authorities, who saw the heliocentric model as a threat to established doctrine. The scientific revolution did not stop with Galileo. Johannes Kepler, using the meticulous observations of Tycho Brahe, discovered that planets move in ellipses, not perfect circles. This insight, published in his 3 Laws of Planetary Motion, provided a mathematical framework for the heliocentric model. Later, Isaac Newton's law of universal gravitation explained why planets move as they do, uniting the physics of the heavens and the Earth for the first time. These advances fundamentally altered our relationship with the cosmos. Earth was no longer the centre, but a planet in motion, governed by the same physical laws as the rest of the universe. The Sun became the centre of our local system, the solar system, a collection of planets, moons, asteroids and comets bound together by gravity. Yet even the Sun was revealed to be just one among hundreds of billions of stars in the Milky Way, a vast spiral galaxy stretching over 100,000 light-years across. This realization led to a new, even more profound question. If our solar system is not the centre of the universe, where exactly are we within the Milky Way? Astronomers began to map the positions of stars, measure their distances, and study the structure of our galaxy, seeking to understand our true cosmic address. Answering this question would require the development of ever more powerful telescopes, new methods of measurement such as parallax and spectroscopy, and a willingness to challenge old assumptions. The journey to find our place in the Milky Way was only just beginning, a journey that would transform our understanding of the universe and our place within it. Once astronomers realized that our Sun is just one of hundreds of billions of stars embedded within a vast disc-shaped collection known as the Milky Way, a new and daunting challenge emerged. How could we possibly map the structure of our own galaxy from the inside out? Unlike observing distant galaxies, where we can see their full shapes from afar, we are trapped within the Milky Way's swirling arms, surrounded by countless stars and thick clouds of cosmic dust. The task is akin to trying to chart the layout of an immense forest while standing deep within its densest thickets. From our vantage point, we cannot simply look down and see the galaxy's spiral arms or its central bulge. Instead, we must rely on indirect clues, piecing together the Milky Way's structure from the light and signals that manage to reach us. This challenge is compounded by the fact that the Milky Way is filled with interstellar dust and gas, which absorb and scatter visible light. These clouds act like a thick fog, obscuring our view and making it nearly impossible to see more than a few thousand light-years in any direction with ordinary telescopes. The very material that gives the Milky Way its breathtaking beauty, its dense, glowing clouds of interstellar gas and dust, also hides its true form. These clouds are composed primarily of tiny solid particles, or dust grains, mixed with cold molecular gas. They absorb and scatter visible light, especially at shorter wavelengths, making the galaxy's core and far-side spiral arms invisible to our eyes. When we point a conventional optical telescope toward the galactic center, the heart of our galaxy, we see only a faint glow. The dense dust clouds block nearly all visible light, allowing us to glimpse just a fraction of the stars and structures that lie beyond. For centuries, the true shape of the Milky Way, its spiral arms, its central bulge, and its overall structure remained a profound mystery. Astronomers could only speculate about what lay hidden behind this cosmic curtain, using the positions and motions of nearby stars as their only clues. To overcome these obstacles, astronomers realized they needed to look beyond visible light. The universe emits radiation across the entire electromagnetic spectrum, from long-wavelength radio waves to short-wavelength gamma rays. Each type of light interacts differently with interstellar dust and gas, offering unique windows into the hidden regions of our galaxy. The breakthrough came in the mid-20th century with the advent of radio astronomy. Unlike visible light, radio waves have much longer wavelengths, allowing them to pass through dust clouds with little absorption or scattering. This opened up an entirely new way to observe the Milky Way. Radio telescopes, with their large parabolic dishes, are designed to collect these faint, long wavelength signals from space. By tuning into specific frequencies, astronomers can detect the unique radio emissions produced by different types of atoms and molecules in the interstellar medium. One of the most important discoveries was the detection of the 21-centimeter line, a specific radio emission produced by neutral hydrogen atoms. Hydrogen is the most abundant element in the universe, and its 21 cm emission allows astronomers to map the distribution of cold, neutral hydrogen gas throughout the Milky Way, even in regions completely hidden from view in visible light. This hydrogen gas is not only the raw material for star formation, but it also traces the spiral arms of the galaxy. By measuring the Doppler shift of the 21 cm line, astronomers can determine the motion of hydrogen clouds, revealing the rotation curve of the Milky Way and the locations of its spiral arms. By painstakingly mapping the positions and velocities of hydrogen clouds across the sky, astronomers were able to reconstruct the grand, swirling pattern of the Milky Way's spiral arms for the first time. This revealed that our galaxy is not a simple, featureless disk, but a magnificent spiral galaxy with multiple arms winding outward from a central core. Another crucial tool in the astronomer's arsenal is infrared astronomy. Infrared light has longer wavelengths than visible light, allowing it to penetrate dust clouds that would otherwise block our view. Many objects in the galaxy, including stars in their earliest stages of formation, emit strongly in the infrared. Infrared radiation is less affected by dust extinction, so infrared telescopes can peer deep into the heart of the Milky Way, revealing stars and structures that are completely invisible in optical wavelengths. This has been especially important for studying the galactic center, where dust is most concentrated. Space-based observatories like the Spitzer Space Telescope and the Infrared Astronomical Satellite, or IRAS, have revolutionized our understanding of the galaxy. By observing in the infrared, these telescopes act like cosmic heat vision goggles, allowing us to see through the dust and uncover the hidden architecture of the Milky Way. Infrared surveys have provided a stunning revelation. At the heart of the Milky Way lies not a simple spherical cluster of stars, but a massive, elongated bar-shaped structure. This bar is composed of older, redder stars and stretches across the central region of the galaxy, influencing the motion of stars and gas throughout the inner Milky Way. This discovery confirmed that the Milky Way is not just a spiral galaxy, but a barred spiral galaxy, a common but striking form seen in many galaxies across the universe. The bar acts as a dynamical engine, funneling gas toward the centre and fueling bursts of star formation and activity around the supermassive black hole at the core. Today, our understanding of the Milky Way's structure is a composite, built from observations across the electromagnetic spectrum. By combining data from radio, infrared, optical, and even X-ray and gamma-ray telescopes, astronomers have assembled a multi-layered portrait of our galaxy, each wavelength revealing different components and processes. We now know that the Milky Way has 4 primary spiral arms: the Norma arm, the Scutum Centaurus arm, the Sagittarius arm, and the Perseus arm. These arms are regions of enhanced star formation, where clouds of gas collapse to form new stars and are traced by the distribution of young, massive stars, star clusters, and glowing nebulae. Our own solar system is not located in one of these major arms, but instead resides in a smaller partial arm or spur known as the Orion arm or Orion spur. This region is nestled between the larger Sagittarius and Perseus arms and is home to many of the bright stars and nebulae visible in our night sky. By combining observations from radio, infrared, X-ray and gamma-ray telescopes, astronomers can study everything from the coldest gas clouds to the hottest, most energetic phenomena in the galaxy. This multi-wavelength approach reveals the full complexity of the Milky Way, from star-forming regions and supernova remnants to the energetic jets and outflows near the central black hole. The intricate map we have today, pieced together from light our eyes can never see, allows us to step outside our cosmic home, at least in our imagination, and appreciate the grand design of the Milky Way. It is a testament to human ingenuity and the power of science that, from our tiny vantage point within a single spiral arm, we have managed to chart the vast and beautiful structure of our galactic city, revealing its secrets one wavelength at a time. Having mapped the broad strokes of the galaxy, we can now pinpoint our own location within this immense structure. The Milky Way, a barred spiral galaxy, is composed of a central bulge, a flat rotating disk of stars, gas and dust, and an encompassing halo of older stars and globular clusters. Our solar system resides about 26,000 light-years away from the bustling, chaotic galactic centre. This central region is dominated by a supermassive black hole known as Sagittarius A*, which exerts a powerful gravitational influence on the surrounding stars and gas. If you imagine the Milky Way's visible disk as being 100,000 light-years across, our position is roughly halfway between the centre and the outer edge. This is a relatively quiet, suburban-like region of the galaxy, far removed from the frenetic activity of the core. We are far enough from the violent activity of the core to have enjoyed billions of years of relative stability, yet close enough to regions of star formation to be supplied with the heavier elements necessary for rocky planets and indeed for life itself. This fortunate positioning has allowed complex life to evolve on Earth. Our journey through the galaxy is not a static one. Just as the Earth orbits the Sun, our entire solar system is in constant motion, orbiting the supermassive black hole at the galactic centre. We are hurtling through space at a staggering speed of approximately 828,000 kilometers per hour, or over 500,000 miles per hour. Even at this incredible velocity, the sheer scale of the Milky Way means that it takes our Sun about 230 million years to complete a single orbit. This vast span of time is sometimes referred to as a galactic year. To put this into perspective, the last time our solar system was in its current position in the galaxy, dinosaurs were just beginning to walk the Earth. Our immediate neighbourhood is known as the Orion arm, or sometimes the Orion spur. It is a minor spiral arm, a smaller branch that connects to the more substantial arms of the galaxy. It is about 3,500 light-years across and roughly 10,000 light-years in length. This arm is home to some of the most famous and recognizable celestial objects in our night sky, including the beautiful Orion Nebula, a massive stellar nursery where new stars are being born. Living within this spur means that when we look out at night, our view is populated by the stars of our local arm, which is why constellations like Orion are so prominent. We are truly embedded within the local fabric of our galaxy. This specific location has profound implications for our view of the universe. Because we are situated within the flat plane of the galactic disk, our view of the wider cosmos is partially blocked by the Milky Way itself. The very band of stars that awed our ancestors creates a zone of avoidance, where distant galaxies are hidden from view behind the dense gas and dust of our own. It is another reminder that our perspective is always shaped by our position. We are travellers on a cosmic carousel, looking out at the universe from a moving platform in a quiet but not entirely isolated corner of a vast and spectacular spiral city of stars. This dynamic journey through the galaxy offers us a unique vantage point, constantly shifting our view and understanding of the cosmos. When we gaze up at the night sky, the stars, planets and glowing clouds of gas and dust seem to tell the whole story of our galaxy. But in reality, all of this visible matter, every shining star, every swirling nebula, every planet and asteroid, accounts for only a tiny sliver of the Milky Way's true mass. This realization is one of the most profound and humbling in all of modern astronomy. In fact, all the matter that interacts with light, the so-called baryonic matter, makes up just about 10 to 15% of the galaxy's total mass. Baryonic matter includes protons, neutrons and electrons, the building blocks of atoms that form everything we can see and touch. The remaining 85 to 90% is composed of something entirely different, an invisible, enigmatic substance known as dark matter. This dark matter does not emit, absorb or reflect electromagnetic radiation, which means it cannot be seen directly with any telescope, no matter how powerful. The very term dark matter is a bit of a misnomer. It's not simply matter that is dark or unlit. It is in fact completely transparent and undetectable by any means except through its gravitational influence. This makes it one of the most elusive components of the cosmos. So how do we know it's there? The answer lies in gravity. Dark matter reveals itself through the gravitational pull it exerts on visible matter, bending the paths of stars, gas, and even light itself. One of the most striking pieces of evidence comes from a phenomenon called gravitational lensing, where the gravity of unseen mass bends the light from distant objects, distorting their appearance in ways that cannot be explained by visible matter alone. But perhaps the most compelling evidence comes from the way stars move within galaxies. In the Milky Way, astronomers have observed that stars in the outer regions are orbiting the galactic centre at speeds that defy expectations. According to Newton's laws of gravity, the farther a star is from the dense centre of the galaxy, the slower it should orbit, just as the outer planets in our solar system, like Neptune and Pluto, move more slowly around the Sun than Mercury or Venus. This is because the gravitational pull weakens with distance, and there is less mass inside the orbit to provide the necessary force. However, when astronomers measured the actual rotation speeds of stars at various distances from the galactic centre, they found something astonishing. Instead of slowing down, the stars in the outer regions were moving just as fast as those closer in. This observation is captured in what's known as the galactic rotation curve, a graph that plots orbital speed against distance from the centre. The observed curve remains flat, rather than dropping off as predicted. This flat rotation curve is a direct violation of the laws of physics as we understand them, unless there is a vast amount of unseen mass providing the extra gravitational pull needed to keep those fast-moving stars from flying off into space. This invisible mass acts as a kind of gravitational glue, binding the galaxy together. The current scientific consensus is that this unseen mass forms a vast, roughly spherical halo that envelops the entire galaxy, extending far beyond the visible disk of stars. This dark matter halo is not just a thin shell, it is a massive three-dimensional structure that dominates the galaxy's gravitational landscape. To put this in perspective, while the luminous part of the Milky Way, the part we can see with telescopes, spans about 100,000 light-years across, the dark matter halo may stretch for over 300,000 light-years in every direction. This means that the true gravitational boundary of our galaxy is much larger and more massive than it appears in visible light. When astronomers estimate the total mass of the Milky Way, they arrive at a figure between 1 and 1.5 trillion times the mass of our Sun. Astonishingly, the vast majority of this mass, upwards of 1 trillion solar masses, comes from dark matter, not from the stars, gas or dust that we can see. In a very real sense, dark matter acts as the invisible scaffolding upon which the entire galaxy is built. Without it, the Milky Way would not have the structure or stability to exist as we know it. The stars and gas would not be able to hold together in a coherent spiral form. Instead, they would disperse into the void. Yet, despite its overwhelming presence, the true nature of dark matter remains one of the greatest unsolved mysteries in all of science. We know it is not made of ordinary atoms, nor does it interact with light or electromagnetic forces in any detectable way. In fact, we know more about what dark matter is not than what it actually is. It is not composed of the familiar protons, neutrons and electrons that make up stars, planets and people. It does not form atoms, nor does it participate in nuclear reactions or chemical bonds. It is also not simply dark clouds of normal matter, such as cold gas or dust, because those would be detectable through their absorption or emission of radio waves, infrared, or other forms of radiation. Careful surveys of the sky have ruled out these possibilities. Instead, physicists have proposed a range of exotic particles as candidates for dark matter. These include weakly interacting massive particles, or WIMPs, which would interact only through gravity and the weak nuclear force, and axions, hypothetical particles that are extremely light and elusive. There are also theories involving sterile neutrinos and other even more exotic possibilities. To search for these particles, scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and other sources of interference. They also use powerful particle accelerators, like the Large Hadron Collider, to try to create dark matter particles in high-energy collisions. Despite decades of effort, no definitive detection has yet been made. The quest to understand dark matter is not just about our own galaxy. Dark matter plays a crucial role in the formation and evolution of the entire universe. It acts as the cosmic scaffolding upon which galaxies and galaxy clusters form, shaping the large-scale structure of the cosmos. Without dark matter, the universe as we know it would look profoundly different. Galaxies might never have formed, and the cosmic web that connects them would not exist. In the end, dark matter remains a gravitational ghost, an invisible yet fundamental component of the universe. Unlocking its secrets will not only reveal the true nature of our galaxy, but also help us understand the origins and fate of the cosmos itself. When we imagine the Milky Way, it's tempting to picture a simple, flat spiral, like a cosmic pinwheel floating serenely in space. But the reality is far more intricate. The Milky Way's true three-dimensional structure is a tapestry woven from billions of years of dynamic processes, gravitational interactions, and the ongoing evolution of its stars and gas. Let's embark on a detailed exploration of the galaxy's bulges, warps and flares, features that reveal the Milky Way's complex and ever-changing nature. At the very heart of our galaxy lies the central bulge, a dense spheroidal region packed with stars. This bulge is dominated by older reddish stars, many of which are more than 10 billion years old. These stars are typically low in heavy elements, or metals, indicating that they formed early in the galaxy's history, before successive generations of supernovae enriched the interstellar medium with heavier elements. For much of the 20th century, astronomers assumed the bulge was a simple, roughly spherical ball of stars, an idea based on early optical observations that were limited by the thick clouds of dust obscuring our view toward the galactic centre. However, the advent of infrared astronomy revolutionized our understanding. Infrared light can penetrate the dust that blocks visible wavelengths, allowing astronomers to peer deep into the galactic core. These observations revealed that the bulge is not spherical at all. Instead, the bulge is elongated, forming a bar-like structure that stretches across the centre of the galaxy. When viewed from the side, this bar gives the bulge a boxy or even peanut-like appearance, a shape that is now recognized as common in many spiral galaxies. Within this bar, the orbits of stars are highly complex. Recent studies using data from missions like the European Space Agency's Gaia satellite have revealed an X-shaped structure embedded within the bar. This X-shape is thought to arise from the orbits of stars that are lifted above and below the galactic plane by resonances in the bar's gravitational potential, a phenomenon known as boxy peanut bulge formation. This structure is a direct consequence of the dynamical evolution of the bar, and its discovery has provided crucial insights into the history of our galaxy's inner regions. Moving outward from the central bar, we encounter the main disk of the Milky Way, a vast rotating structure composed of stars, gas and dust. This is where our solar system is located, about 27,000 light-years from the galactic centre. The disk is the site of ongoing star formation, with spiral arms rich in young, hot blue stars, as well as giant molecular clouds that serve as stellar nurseries. Contrary to the common depiction of a perfectly flat disk, the Milky Way's disk is subtly curved. This curvature is not just a minor detail, it's a clue to the dynamic forces at play within and around our galaxy. As we move toward the outer edges of the disk, this curvature becomes a pronounced warp. The galactic disk bends upward on one side and downward on the other, creating a shape reminiscent of a warped vinyl record. To visualize this, imagine a spinning vinyl record that's been left in the sun too long. The heat causes the record to warp, so one edge curves up while the opposite edge curves down. The Milky Way's disk exhibits a similar though much grander distortion. This galactic warp is not a minor feature. It's a dramatic large-scale deformation that extends tens of thousands of light-years from the galactic centre. The warp is most prominent in the outer disk, where the density of stars and gas drops off, making the structure more susceptible to external influences. What causes this warp? The leading explanation involves the gravitational influence of our galaxy's neighbours, particularly the large and small Magellanic Clouds. These are dwarf satellite galaxies that orbit the Milky Way. As they pass by, their gravity tugs on the outer regions of our disk, setting up oscillations that manifest as a warp. Recent computer simulations suggest that the Magellanic Clouds may be on their first close approach to the Milky Way, and their massive dark matter halos could be amplifying the warp's amplitude. In addition to being warped, The galactic disk also exhibits a phenomenon known as flaring. This means that the thickness of the disk increases as you move away from the centre. Near the Sun, the disk is relatively thin, about 1,000 light-years thick. But as you travel outward, the disk becomes progressively thicker, or flared, reaching several thousand light-years at the periphery. This flaring is observed in both the stellar and gaseous components of the disk. To put this in perspective, if you were to compare the thickness of the disk near the Sun to its thickness at the outermost regions, you'd see a dramatic increase, sometimes by a factor of 3 or more. This is not just a geometric curiosity. It has profound implications for the dynamics and evolution of the galaxy. The flaring of the disk is thought to result from a process called dynamic heating. Over billions of years, gravitational interactions, both internal, such as spiral arm instabilities, and external, such as encounters with satellite galaxies, cause the orbits of stars in the outer disk to become more eccentric and inclined. This puffs up the disk, making it thicker at greater distances from the centre. The result is a disk that is not a uniform, flat structure, but one that resembles a flared trumpet bell at its edges. This shape affects how gas flows through the galaxy, how stars form, and even how the Milky Way interacts with its environment. When we put all these features together, the peanut-shaped bulge, the warped disk, and the flared edges, we see a galaxy that is anything but static. Each of these structures is a record of the Milky Way's dynamic history, shaped by both internal processes and external encounters. Over cosmic time, the Milky Way has been sculpted by a combination of internal dynamics, such as the formation and evolution of the bar, spiral arms and star clusters, and external forces, including mergers with smaller galaxies and the gravitational pull of its satellite companions. These processes leave their imprint on the galaxy's structure, creating the complex three-dimensional shape we observe today. The distribution and motion of hundreds of billions of stars, as well as vast clouds of gas and dust, encode the Milky Way's history. By studying the detailed structure of the bulge, the warp, and the flare, astronomers can reconstruct the sequence of events that have shaped our galaxy, from its formation in the early universe to its ongoing interactions with neighbouring galaxies. Each warp, bulge, and flare is a chapter in the Milky Way's story, a testament to the relentless influence of gravity, the power of cosmic collisions, and the ceaseless evolution of galaxies across billions of years. The Milky Way is not just our home in the cosmos. It is a living, breathing system, shaped by the forces of nature and the passage of time. At the very centre of our galaxy, shrouded by thick, impenetrable clouds of interstellar gas and dust, lies the most extreme and mysterious object in the Milky Way, a supermassive black hole. This region is so heavily obscured in visible light that for centuries its true nature remained hidden from astronomers, only to be revealed through the use of infrared and radio telescopes capable of peering through the cosmic fog. This central zone is often referred to as the galactic engine room. Here, the density of matter and the concentration of energy reach levels that are almost unimaginable. The gravitational forces at play are so intense that they shape the very structure and dynamics of the entire galaxy, influencing the orbits of stars, clouds of gas, and even the distribution of dark matter. Within this tumultuous environment, we find the most crowded star clusters in the Milky Way, such as the Arches and quintuplet clusters. These clusters are home to some of the most massive and luminous stars known, packed together millions of times more densely than the stars in our own solar neighbourhood. The intense radiation and stellar winds from these stars create a dynamic, ever-changing environment where new stars are born and old ones are torn apart by gravitational tides. At the very heart of this chaos sits Sagittarius. A contains a mass equivalent to about 4 million suns. Yet all of this mass is compressed into a region smaller than the orbit of Mercury around our Sun. The concept of a black hole arises from Einstein's general theory of relativity, which predicts that when a massive enough object collapses under its own gravity, it warps space-time so severely that nothing, not even light, can escape its grasp. Directly observing a black hole is impossible, since its event horizon marks the boundary beyond which no information can escape. Instead, astronomers infer its presence by studying the gravitational effects it exerts on its surroundings. The stars and gas clouds near Sagittarius A** move at extraordinary speeds, their orbits twisted and accelerated by the immense gravitational pull of the black hole. For decades, teams of astronomers have used advanced infrared telescopes, such as those at the Keck Observatory and the Very Large Telescope, to track the precise motions of individual stars near the galactic center. By mapping these orbits with exquisite accuracy, they have been able to reconstruct the invisible gravitational landscape sculpted by Sagittarius A*. One of the most remarkable discoveries is the star known as S2. This star follows a highly elliptical orbit around Sagittarius A*, completing a full revolution every 16 years. At its closest approach, S2 hurtles through space at speeds exceeding 25 million kilometers per hour, fast enough to travel from Earth to the Moon in less than a minute. The only force capable of keeping S2 in such a tight, rapid orbit is the gravity of a supermassive black hole. The gravitational influence required to bind S2 and other nearby stars to such compact orbits cannot be explained by any visible matter, such as clusters of stars or clouds of gas. Only a single, incredibly massive and compact object, Sagittarius A, fits the data. This conclusion is further supported by the absence of any detectable light or radiation from the region that would be expected if the mass were distributed among many smaller objects. The precise mapping of these stellar orbits provided the definitive, irrefutable evidence for the existence of a supermassive black hole at the center of our galaxy. This achievement was recognized with the 2020 Nobel Prize in Physics, awarded to Reinhard Genzel and Andrea Ghez for their pioneering work in this field. In 2022, the Event Horizon Telescope collaboration achieved a historic milestone by capturing the first-ever direct image of Sagittarius A*. This global network of radio telescopes, operating in perfect synchronization, effectively created a virtual telescope the size of the Earth, capable of resolving details at the scale of the black hole's event horizon. The resulting image doesn't show the black hole itself, but rather its shadow, a dark central region surrounded by a glowing ring of superheated gas and plasma. This ring forms as matter spirals inward, heated to billions of degrees by friction and gravitational compression, emitting intense radio waves just before it crosses the event horizon and disappears forever. The luminous ring seen in the image is a direct consequence of the extreme physics near the event horizon. As matter accelerates to nearly the speed of light, it emits powerful radiation, and the warping of space-time by the black hole's gravity bends the paths of these photons, creating the distinctive shadow and ring structure predicted by Einstein's equations. Capturing this image required an unprecedented level of international cooperation and technological innovation. The Event Horizon Telescope Array combined data from observatories on multiple continents using a technique called very long baseline interferometry to achieve the necessary resolution. The data processing alone took years, involving sophisticated algorithms to reconstruct the image from petabytes of raw observations. The image of Sagittarius A** provided a stunning visual confirmation of the predictions made by general relativity. The size and shape of the shadow matched theoretical models with remarkable precision, offering new insights into the behaviour of gravity in its most extreme form, and placing stringent limits on alternative theories of physics. Despite its immense power, Sagittarius A* is currently in a relatively quiescent state. Unlike the supermassive black holes at the centres of some other galaxies, which devour vast amounts of matter and unleash powerful jets of energy, our galaxy's black hole is comparatively quiet, accreting only small amounts of gas and dust. Occasionally, Sagittarius A* flares up, emitting bursts of X-rays and infrared light when a small gas cloud or an unlucky star ventures too close and is torn apart by tidal forces. These flares provide astronomers with valuable opportunities to study the physics of accretion and the behavior of matter under the most extreme conditions known in the universe. However, evidence suggests that Sagittarius A* was far more active in the distant past. During its more energetic phases, it likely shaped the evolution of the entire galactic centre, driving powerful outflows of gas, triggering bursts of star formation, and influencing the distribution of matter on a galactic scale. The feedback from such activity may have played a crucial role in regulating the growth of the Milky Way itself. Today, Sagittarius A* acts as a gravitational anchor for the Milky Way, its immense mass holding together the orbits of billions of stars and providing stability to the galaxy's structure. It is a silent, sleeping giant at the heart of our vast stellar city. Its presence felt across tens of thousands of light-years. The ongoing study of Sagittarius A* continues to push the boundaries of our understanding of gravity, quantum mechanics, and the fundamental laws of the universe. Each new observation brings us closer to unraveling the mysteries of black holes, the nature of space-time, and the origins of the cosmos itself. As technology advances, the heart of our galaxy will remain a focal point for scientific discovery, inspiring generations to look up and wonder at the profound forces shaping our universe. While the supermassive black hole at the heart of our galaxy, known as Sagittarius A*, appears dormant today, astronomers have uncovered compelling evidence that it once experienced episodes of extraordinary violence and activity. This evidence is not found in the visible stars or swirling clouds of gas, but in vast, mysterious structures that stretch far above and below the galactic plane, silent witnesses to a tumultuous past. In 2010, using the Fermi Gamma-ray Space Telescope, scientists detected two enormous hourglass-shaped lobes of high-energy emission, now known as the Fermi bubbles. These structures extend approximately 25,000 light-years, both above and below the centre of the Milky Way, dwarfing the visible disk of our galaxy and challenging our understanding of galactic dynamics. The Fermi bubbles are invisible to optical telescopes and the naked eye, but they shine intensely in gamma rays, the most energetic form of electromagnetic radiation. Gamma rays are produced by some of the universe's most extreme processes, such as the acceleration of charged particles to near-light speeds, supernova explosions, and the energetic outflows from black holes. Each bubble spans an astonishing 25,000 light-years from the galactic centre, making the total structure nearly 50,000 light-years tall, almost half the diameter of the entire Milky Way's stellar disk. To put this in perspective, if our solar system were a single grain of sand, the Fermi bubbles would be the size of a mountain looming above and below it. These ghostly, balloon-like structures are relics of a cataclysmic event, or series of events that released an immense amount of energy from the galactic centre. Their sharp edges and uniform brightness suggest a sudden, powerful origin rather than a slow, gradual process. Astronomers believe the Fermi bubbles are the after-effects of a massive outburst of energy that erupted from the galactic core millions of years ago. The energy required to inflate these bubbles is estimated to be equivalent to the simultaneous explosion of hundreds of thousands of supernovae, or the output of a quasar, a galaxy with an actively feeding supermassive black hole. There are two leading scientific theories that attempt to explain the origin of the Fermi bubbles, each pointing to a different kind of cosmic upheaval in the Milky Way's past. The first theory suggests that the bubbles were created by a period of intense star formation known as a starburst near the galactic center. During a starburst, the rate of star birth can be dozens or even hundreds of times higher than normal, leading to the formation of massive, short-lived stars. These massive stars rapidly exhaust their fuel and end their lives in spectacular supernova explosions. The combined effect of their powerful stellar winds and the shock waves from thousands of supernova could have swept up and heated vast amounts of gas, blasting it out of the galactic plane and inflating the giant lobes we now observe as the Fermi bubbles. Such an event would have resembled a cosmic firework display on a scale almost impossible to imagine, with energy and matter being hurled into the galactic halo, shaping the environment for millions of years and possibly triggering further waves of star formation. The second, and perhaps more widely supported explanation, implicates the supermassive black hole itself. Sagittarius A*, with a mass over 4 million times that of our Sun, is usually quiet. But black holes can go through active phases when they devour large amounts of gas and dust. In this scenario, the Fermi bubbles are the fossil remains of a time when Sagittarius A* was actively accreting matter. As material spiraled into the black hole, it formed a superheated accretion disk, generating intense magnetic fields and launching twin jets of high-energy particles perpendicular to the disk. These jets, composed of electrons and protons accelerated to nearly the speed of light, would have blasted through the surrounding gas, inflating the enormous cavities we now see as the Fermi bubbles. This process is similar to what we observe in active galactic nuclei and quasars in other galaxies, where black holes are seen shaping their host galaxies on colossal scales. The jets would have carved out vast regions of hot, low-density plasma, pushing aside cooler gas and leaving behind the sharp-edged gamma-ray bright structures that define the Fermi bubbles today. This evidence suggests that the Milky Way's center was once as active and luminous as the quasars we see in the distant universe, with Sagittarius A*, briefly shining as a beacon visible across cosmic distances. Regardless of their exact origin, the Fermi bubbles are now recognized as a crucial component of the Milky Way's galactic weather system. They are not static relics, but dynamic structures that interact with the surrounding interstellar medium, influencing the flow of energy and matter throughout the galaxy. The bubbles participate in a complex cycle of galactic winds, shock waves, and feedback processes that regulate star formation, redistribute heavy elements, and help shape the evolution of the Milky Way. They serve as conduits for energy transfer between the dense galactic disk and the more diffuse halo, driving turbulence and mixing material on a galactic scale. The presence of the Fermi bubbles reveals that the space above and below the Milky Way is far from empty. Instead, it is filled with the echoes of ancient outbursts, hot plasma, cosmic rays, and magnetic fields that continue to ripple through the galactic halo, carrying the memory of past events. The discovery and ongoing study of the Fermi bubbles have revolutionized our understanding of the Milky Way's history. They provide direct evidence that our galaxy, now relatively calm, once experienced episodes of extreme violence and transformation. These invisible structures, glowing only in the highest energies, are a cosmic record, etched across the sky in gamma rays, of a time when the heart of the Milky Way blazed with unimaginable power, shaping the galaxy we see today. Galaxies like our Milky Way are not static, monolithic structures that have existed unchanged since the dawn of the universe. Instead, they are dynamic, evolving systems shaped by a complex history of interactions, mergers and accretion events that span billions of years. The process by which galaxies grow and evolve is known as hierarchical assembly, a fundamental concept in modern cosmology. In this model, small protogalactic fragments formed first, soon after the Big Bang, and gradually merged to build up larger galaxies over cosmic time. One of the most dramatic mechanisms driving this growth is galactic cannibalism. This term refers to the process by which a large galaxy, such as the Milky Way, gravitationally captures and assimilates smaller satellite galaxies that venture too close. The immense gravitational pull of the larger galaxy disrupts the structure of the smaller one, stripping away its stars, gas and dark matter, and incorporating them into its own halo and disk. This is not a rare or isolated event. Astronomers have identified numerous stellar streams and substructures in the Milky Way's halo, each one a remnant of a past galactic meal. The evidence for this cosmic predation is written across the sky. The outer regions of the Milky Way are crisscrossed with faint, elongated streams of stars. These are the tidal remnants of galaxies that have been torn apart by our galaxy's gravity. These stellar streams are not only visually striking, but they also serve as fossil records, preserving the orbital paths and chemical signatures of their progenitor galaxies. By mapping and analysing these streams, astronomers can reconstruct the Milky Way's merger history, piecing together a timeline of past collisions and accretion events. The process of tidal disruption is governed by the interplay of gravitational forces. As a dwarf galaxy approaches the Milky Way, the difference in gravitational pull between its near and far sides, known as tidal forces, stretches the smaller galaxy, eventually pulling it apart. The stars and dark matter that once belonged to the dwarf are spread out along its orbit, forming long flowing ribbons that can wrap around the Milky Way multiple times. These streams can persist for billions of years, gradually mixing with the stars of the host galaxy. One of the most prominent and well-studied examples of this process is the ongoing disruption of the Sagittarius dwarf spheroidal galaxy. Discovered in the 1990s, the Sagittarius dwarf is currently being torn apart by the Milky Way's gravity. Its stars are being stripped away to form the Sagittarius stream, a vast, looping river of stars that encircles our galaxy. Detailed observations and simulations have shown that the Sagittarius dwarf has already passed through the Milky Way's disk several times, each passage triggering waves and ripples in the galactic disk, and possibly even influencing the rate of star formation in our region of space. The study of these stellar streams has been revolutionized by the European Space Agency's Gaia mission. Launched in 2013, Gaia is mapping the positions, motions and properties of over 1 billion stars in the Milky Way with unprecedented precision. This wealth of data allows astronomers to identify and characterize stellar streams, measure their orbits, and trace them back to their origins. By combining Gaia's data with computer simulations, researchers have been able to identify major merger events in the Milky Way's past, such as the Gaia-Enceladus or sausage merger, which occurred about 10 billion years ago and contributed a significant fraction of the stars in the galactic halo. The hierarchical assembly of the Milky Way is an ongoing process. Our galaxy is surrounded by dozens of smaller satellite galaxies, many of which are destined to be assimilated in the future. But the most dramatic event in the Milky Way's future is the impending collision with the Andromeda Galaxy, the other giant spiral in our local group. Andromeda, also known as M31, is located about 2.5 million light-years away, and is moving towards us at a speed of roughly 400,000 kilometers per hour. Precise measurements of its motion, including its tangential velocity, have confirmed that the two galaxies are on a direct collision course. This cosmic rendezvous is expected to begin in about 4 billion years. As the Milky Way and Andromeda approach each other, their mutual gravitational attraction will draw them together, initiating a complex and spectacular sequence of events. Despite the vast number of stars in each galaxy, hundreds of billions, the distances between individual stars are so great that direct stellar collisions will be exceedingly rare. Instead, the galaxies will pass through each other, their shapes distorted by tidal forces, flinging out long tails of stars and gas. Over the course of several close encounters, the two galaxies will lose angular momentum through dynamical friction, a process in which the gravitational interactions between stars and dark matter slow down their relative motion. This will cause the galaxies to spiral closer together, eventually merging into a single, much larger galaxy. Simulations suggest that the final product will be an elliptical galaxy, sometimes referred to as Milky Way. The spiral arms of both progenitor galaxies will be destroyed, and the new galaxy will have a more featureless reddish appearance, as the gas needed for new star formation will be largely exhausted. The merger will have profound effects on the structure and dynamics of the resulting galaxy. The supermassive black holes at the centers of the Milky Way and Andromeda will eventually coalesce, releasing enormous amounts of energy in the form of gravitational waves. The orbits of stars, including our own Sun, will be radically altered. Some may be flung into the outer halo, while others may be drawn closer to the galactic center. The night sky, as seen from any surviving planets, will be transformed, first by the growing presence of Andromeda, then by the chaotic intermingling of stars, gas and dust as the galaxies merge. This grand collision is not unique to our local group. Galactic mergers are a fundamental driver of galaxy evolution throughout the universe. They play a crucial role in shaping the morphology, star formation history, and chemical composition of galaxies. By studying mergers both near and far, astronomers gain insight into the processes that have shaped the cosmos on the largest scales. Ultimately, the story of the Milky Way is one of constant change, a cosmic dance of creation and destruction, driven by the relentless pull of gravity. Our galaxy is not an isolated island, but an active participant in the ongoing evolution of the universe, shaped by its interactions with its neighbours and destined for a spectacular future as part of a new merged galaxy. When we gaze up at the night sky, we are peering into a vast cosmic ocean containing hundreds of billions of stars, each potentially hosting its own planetary system. Recent advances in astronomy, particularly through missions like Kepler and TESS, have revealed that planets are not rare exceptions, but rather the rule. Most stars are now believed to have at least one planet, and many have multiple. This realization has transformed one of humanity's oldest questions, are we alone, from a matter of philosophy to one of scientific investigation. The search for life beyond Earth, known as astrobiology, is a multidisciplinary field that draws from astronomy, biology, chemistry, and planetary science. Astrobiologists examine not only the conditions necessary for life as we know it, liquid water, organic molecules and energy sources, but also the broader cosmic environments that might foster or hinder the emergence and evolution of life. This leads us to consider which regions of our galaxy might be most conducive to the development of complex, multicellular organisms and even intelligent civilizations. This line of inquiry has given rise to the concept of the Galactic Habitable Zone, or GHZ. The GHZ is a theoretical annular region within the Milky Way where conditions are thought to be just right for life to arise and persist over billions of years. But what makes one part of the galaxy more suitable for life than another? The GHZ is defined by a delicate balance of factors too close to the galactic center, and the environment becomes hazardous due to high stellar densities, frequent supernovae, and intense radiation. Too far from the center, and the abundance of heavy elements, what astronomers call metals, drops off, making it difficult for rocky planets and complex chemistry to form. The GHZ is thus a zone of cosmic compromise, where the opportunities for life are maximized and the dangers minimized. It is not a sharply defined boundary, but rather a region where the probabilities for life-supporting conditions are highest. Let's examine the inner regions of the Milky Way. Here, stars are packed much more closely together than in our solar neighborhood. This high density increases the likelihood of catastrophic events, such as close stellar encounters that can disrupt planetary orbits, or the passage of stars through dense molecular clouds that can trigger comet showers and mass extinctions. Most significantly, the inner galaxy is a hotbed for supernovae, massive stellar explosions that release enormous amounts of radiation and energetic particles. These events can sterilize entire regions, stripping away planetary atmospheres and destroying complex organic molecules. The frequency of such explosions is much higher near the core, making it a perilous place for life to gain a foothold. The galactic center itself is dominated by a supermassive black hole, Sagittarius A*, whose immense gravity and energetic outbursts can disrupt the orbits of stars and planets. The region is also bathed in intense X-ray and gamma-ray radiation, further reducing the chances for stable, long-term habitability. On the other hand, the outermost regions of the Milky Way present a different set of challenges. Here, the density of stars drops off dramatically, and with it, the frequency of supernovae and other catastrophic events. However, these regions are also poor in heavy elements, which are essential for the formation of rocky planets and the complex chemistry required for life. Heavy elements like carbon, oxygen and iron are produced in the cores of massive stars and distributed throughout the galaxy by supernova explosions. These elements are the building blocks of terrestrial planets, as well as the molecules that make up living organisms. In the outer galaxy, where fewer generations of stars have lived and died, the abundance of these elements is much lower. As a result, the outer galaxy may be too chemically impoverished to support the formation of Earth-like planets, let alone complex life. The lack of metals means fewer solid planets, and those that do form may be small, icy, or lacking in the essential ingredients for biology. Our own solar system is situated in a region of the galaxy that appears to be just right, a cosmic Goldilocks zone. We are far enough from the core to avoid the worst hazards, yet close enough to benefit from the heavy elements produced by previous generations of stars. This location has allowed our planet to form, retain its atmosphere, and develop the complex chemistry necessary for life. We occupy a sweet spot, safely distant from the galactic center's chaos, yet in a region enriched by billions of years of stellar evolution. This has led some scientists to propose the rare Earth hypothesis, which suggests that our location may be unusually favorable, and perhaps even necessary for the emergence of complex life. The idea that our position is not merely fortunate, but perhaps a prerequisite for our existence, raises profound questions about the frequency and distribution of life in the galaxy. Are there many other sweet spots, or is our situation truly exceptional? The discovery of exoplanetary systems like TRAPPIST-1, where multiple rocky worlds orbit within their star's habitable zone, has revolutionized our understanding of planetary diversity. Astronomers now use sophisticated techniques such as transit photometry, radial velocity measurements and direct imaging to detect and characterize these distant worlds. By analyzing their atmospheres for gases like oxygen, methane and water vapor, we are searching for potential biosignatures, chemical clues that might indicate the presence of life. Yet, Despite the vastness of the Milky Way and the apparent abundance of habitable worlds, we are confronted by the Fermi paradox. If life is common and intelligent civilizations are possible, why have we not detected any evidence of their existence? The paradox is sharpened by the fact that given the age of the galaxy, even a slow-moving civilization could have colonized it many times over. Scientists have proposed a wide range of possible answers, some optimistic, others unsettling. Perhaps intelligent life is exceedingly rare, or perhaps technological civilizations tend to self-destruct before they can spread. Maybe advanced societies choose to remain silent, or use communication methods beyond our current understanding. It's also possible that we are simply not listening in the right way, or that the timescales of civilizations rarely overlap. One hypothesis is that we are among the first intelligent species to emerge, and that the galaxy is only now becoming hospitable to complex life. Alternatively, civilizations may rise and fall so quickly on cosmic timescales that the odds of two existing at the same time are vanishingly small. Another possibility is that advanced civilizations deliberately conceal their presence, either out of caution or for reasons we cannot yet imagine. This is sometimes called the zoo hypothesis, suggesting that Earth is being deliberately isolated or observed. Or perhaps the development of advanced technology inevitably leads to self-destruction through war, environmental collapse, or other existential risks. This great filter may lie ahead of us, or we may have already passed it. Whatever the answer, our quest to explore the heart of the Milky Way is also a journey to understand our own place in the universe. Through projects like SETI, we are listening for the faintest whispers from distant civilizations, scanning the cosmic river of stars for any sign that we are not alone. Each new discovery, whether of a distant exoplanet or a mysterious radio signal, brings us closer to answering the age-old question of whether we have neighbours among the stars, or whether, for now, we are the only ones looking up and wondering. When we imagine the Milky Way, the image that often comes to mind is that of a majestic spiral, vast arms swirling outward from a bright central core, weaving a cosmic tapestry across the darkness. But what are these spiral arms, truly? And how do they shape the destiny of stars, planets, and perhaps even life itself? The spiral arms of our galaxy are not solid structures, nor are they made up of fixed groups of stars. Instead, they are like traffic jams in the grand highway of the galaxy, regions of higher density that move through the galactic disk, gathering gas, dust, and stars in their wake. As the galaxy rotates, these density waves compress clouds of gas and dust, igniting bursts of star formation that light up the arms like glowing beads on a string. The youngest, brightest stars, hot blue giants, trace out the arms, while older stars drift away over time, blending into the background. Our solar system sits between two of these spiral arms, the Sagittarius arm and the Perseus arm, nestled in a minor spur known as the Orion arm or Orion spur. This location offers us a unique vantage point. From Earth, the arms blend together, forming the luminous band across the night sky that gives our galaxy its name. But the spiral arms are far more than just a spectacular backdrop. They are engines of galactic evolution, orchestrating the life cycles of stars. Within these arms, giant molecular clouds collapse under their own gravity, giving birth to new stars and planetary systems. Over millions of years, the arms sculpt the distribution of matter, recycling gas and dust through generations of stellar birth and death. The shape and structure of the Milky Way's arms have been mapped using a combination of radio, infrared and optical observations, each wavelength revealing a different facet of the galaxy's hidden architecture. Radio telescopes trace the cold hydrogen gas that outlines the arms' skeletons, while infrared surveys pierce through dust lanes to expose newborn stars. These maps reveal a complex, asymmetrical structure: 4 major arms, several minor spurs, and a central bar that twists through the heart of the galaxy. Spiral arms are also home to some of the most dramatic phenomena in the galaxy. Massive star clusters, glowing nebulae, and the remnants of supernovae are concentrated within these regions, shaping the interstellar environment. The arms are cradles of both creation and destruction, where new worlds are born and old ones are swept away by cosmic forces. Yet the existence and persistence of spiral arms remain an active area of research. Are they long-lived features, or do they come and go over billions of years? Some theories suggest that interactions with satellite galaxies or dark matter substructures may periodically trigger the formation of new arms, reshaping the galaxy's appearance over cosmic time. For astronomers, the spiral arms are not just a curiosity, they are a roadmap to understanding our galaxy's past and future. By studying their structure and dynamics, we learn how galaxies like ours grow, evolve, and seed the cosmos with the ingredients for life. As we continue to map the Milky Way in ever greater detail, the spiral arms remind us that our home is not a static island in space, but a living, breathing system, one whose elegant curves and hidden currents have shaped the story of our solar system, and perhaps countless others across the eons. Beyond the luminous spiral arms and bustling galactic disk lies a realm far less familiar, a vast, invisible shroud enveloping the Milky Way. This is the galactic halo, a nearly spherical region that extends far above and below the plane of the galaxy, reaching out to distances over 100,000 light-years from the centre. Though it appears empty to our eyes, the halo is a silent archive, holding clues to the earliest days of our galaxy. Most of the halo's mass is invisible. It's dominated by dark matter, a mysterious, unseen substance that outweighs all the stars, gas and dust in the galaxy combined. Dark matter cannot be seen or touched, but its gravitational pull is unmistakable. It shapes the motion of stars and the rotation of the galaxy, binding the Milky Way together in a cosmic embrace. Without this hidden mass, the spiral arms and disk would simply fly apart. Yet the halo is not entirely empty. Scattered throughout this vast expanse are ancient stars, some among the oldest in the universe. These are the halo stars, faint, metal-poor and long-lived, relics from a time before the Milky Way took its familiar shape. Many of them travel on elongated orbits, plunging through the galactic disk and then soaring high above, tracing paths that reveal the turbulent history of our galaxy's formation. Embedded within the halo are dozens of globular clusters, spherical swarms of hundreds of thousands of stars, tightly bound by gravity. These clusters are like cosmic fossils, their stars formed more than 10 billion years ago. Their orbits and chemical compositions offer vital clues to the Milky Way's earliest mergers and collisions, hinting at a chaotic youth marked by the cannibalization of smaller galaxies. The halo is also home to an array of stellar streams, long, faint rivers of stars stretching across the sky. These streams are the remnants of dwarf galaxies and clusters that ventured too close to the Milky Way and were torn apart by its tidal forces. By mapping these streams, astronomers can reconstruct the Milky Way's history of cosmic encounters and better understand the elusive distribution of dark matter. But perhaps the most mysterious component of the halo is its hot, diffuse gas. This tenuous plasma, invisible to optical telescopes, glows faintly in X-ray light. It may contain as much mass as all the stars in the galaxy, forming a vast, hidden reservoir that influences the Milky Way's ability to form new stars. The origins and fate of this hot halo gas remain an open question, as does its role in the ongoing evolution of our galaxy. Exploring the halo is a challenge that pushes the limits of modern astronomy. Its faint stars and ghostly structures can only be detected with the most sensitive instruments, wide-field surveys, powerful spectrographs and space telescopes tuned to see the invisible. Yet, each new discovery brings us closer to understanding not just the Milky Way, but the cosmic web of galaxies that fills the universe. The galactic halo is a frontier that surrounds us, unseen but ever present. It is a place where the past and future of our galaxy are written in starlight and shadow, a reminder that even in the vastness beyond the familiar, the Milky Way holds mysteries still waiting to be revealed. While the Milky Way dominates our night sky with its sprawling arms and hidden halo, it does not travel the cosmos alone. Surrounding our galaxy is a retinue of smaller companions, dozens of satellite galaxies, each with their own histories, mysteries and roles in shaping the fate of our galactic home. The two most prominent of these are the large and small Magellanic Clouds. Visible to the naked eye from the southern hemisphere, these irregular galaxies are not mere ornaments in our sky. They are dynamic, evolving neighbours, bound to the Milky Way by gravity and locked in a slow, intricate dance. Streams of gas, like the Magellanic Stream and the Leading Arm, arc between these clouds and our galaxy, testifying to a history of close encounters and gravitational tug-of-wars. These rivers of hydrogen fuel, ongoing star formation within the Milky Way's disk, providing the raw material for new generations of stars. But the Magellanic Clouds are just the beginning. Fainter and more elusive are the spheroidal dwarf galaxies, tiny ancient systems like the Sagittarius dwarf, Fornax and Sculptor. These galaxies, some containing just a few million stars, are scattered in a vast invisible sphere around the Milky Way. Many are so faint that they were only discovered in the last few decades, revealed by deep sky surveys and painstaking analysis. Their orbits are often chaotic, shaped by the powerful gravity of our galaxy, and many are being torn apart, leaving behind long, ghostly streams of stars that wrap around the Milky Way like cosmic fingerprints. These satellites are more than passive companions. Their repeated passages through the Milky Way's halo can trigger waves of star formation, disturb the galactic disk, and even warp its structure. The ongoing merger with the Sagittarius dwarf galaxy, for example, has sent ripples through the Milky Way's stars, subtly reshaping its spiral arms and possibly influencing the distribution of dark matter. The satellite galaxies are also cosmic laboratories, offering astronomers a glimpse into the processes that govern galaxy formation and evolution on the smallest scales. Their stars are often much older and less chemically enriched than those in the Milky Way, preserving a record of the early universe. By studying the chemical fingerprints and motion of these stars, scientists can trace the assembly history of our galaxy, uncovering clues about ancient collisions, mergers, and the gradual build-up of the Milky Way's mass. Yet, a mystery remains. The number of satellite galaxies observed around the Milky Way is far fewer than predicted by simulations of dark matter. This missing satellites problem hints at new physics, or perhaps at populations of ultra-faint galaxies yet to be discovered, hidden in the shadows of our galaxy's halo. As our instruments grow more sensitive and our surveys more comprehensive, the census of the Milky Way's companions continues to grow. Each new satellite found adds a piece to the puzzle, helping us understand not just the Milky Way's past, but the intricate web of relationships that binds galaxies together across the universe. The satellite galaxies are silent witnesses to billions of years of cosmic history, companions, rivals and contributors to the ever-evolving story of the Milky Way. Between the blazing stars and spiralling arms of the Milky Way lies a realm often overlooked, a vast complex tapestry known as the interstellar medium. This is not empty space, but a cosmic ocean composed of gas, dust, magnetic fields and cosmic rays, stretching across the galaxy and shaping its destiny in subtle but profound ways. The interstellar medium, or ism, is the birthplace and the graveyard of stars. Here, immense clouds of hydrogen and helium drift silently, some spanning hundreds of light-years. Within these clouds, pockets of gas collapse under their own gravity, kindling the nuclear fires that will become new stars. As these stars evolve and eventually die, some in spectacular supernova explosions, they return their enriched material to the ISM, seeding it with heavier elements like carbon, oxygen and iron. But the ISM is far from uniform. It is a patchwork of phases: cold, dense molecular clouds where stars are born, warm, diffuse regions filled with ionized gas, and hot, thin plasma heated by the shockwaves of dying stars. Invisible magnetic fields thread through these clouds, guiding the flow of charged particles and sculpting the formation of new structures. Cosmic rays, high-energy particles accelerated by supernova, race through the ISM, influencing the chemistry and temperature of the gas. Dust grains, tiny solid particles of carbon and silicates, float through this medium, absorbing and scattering starlight. These grains are the reason why distant stars appear redder and dimmer, and why the heart of the Milky Way is shrouded in mystery when viewed in visible light. Yet, in the infrared and radio wavelengths, astronomers can peer through the dust, revealing hidden nurseries of stars and the intricate filaments of gas that weave the galaxy together. The ISM is also a dynamic environment, constantly stirred by the energy of young stars and supernova. Stellar winds and shock waves carve out vast bubbles and cavities, compressing nearby clouds and triggering new waves of star formation. This feedback loop drives the ongoing evolution of the Milky Way, setting the pace for how quickly it can turn gas into new generations of stars. But the interstellar medium is not just a backdrop, it is a living ecosystem, rich with organic molecules, some of which are the building blocks of life. Complex compounds like polycyclic aromatic hydrocarbons drift between the stars, hinting at the potential for chemistry far beyond our solar system. As we map the ISM with ever greater detail, using radio telescopes, infrared observatories and X-ray satellites, we uncover a hidden world, one that binds stars, planets and life itself into a single cosmic story. The interstellar medium is the connective tissue of the Milky Way, a place where past and future, destruction and creation are forever entwined. In the silent spaces between the stars, the true heartbeat of our galaxy echoes, ever-changing, ever-renewing, and filled with the promise of new beginnings. At the very core of the Milky Way lies a region so dense, so energetic and so enigmatic that it defies easy understanding, a place astronomers simply call the Galactic Centre. Hidden behind billowing clouds of interstellar dust, this cosmic crossroads sits about 26,000 light-years from Earth, in the constellation Sagittarius. Here, the ordinary rules of galactic life are amplified, distorted and sometimes shattered by forces on a scale unimaginable elsewhere in our galaxy. The Galactic Centre is a maelstrom of activity. Packed into a region just a few light-years across are millions of stars, star clusters, swirling clouds of gas, and the supermassive black hole known as Sagittarius A*. Temperatures soar, magnetic fields twist and snap, and gravity reigns supreme. The density of stars here is so high that if you stood on a planet near the core, the night sky would blaze with hundreds of times more starlight than we see from Earth. This bustling hub is not just a stellar metropolis, it's a laboratory for some of the universe's most extreme phenomena. Massive, fast-moving stars, some 20 or 30 times the mass of our Sun, race through the centre, their orbits warped by the black hole's immense gravity. These so-called S-stars have become cosmic test subjects, allowing scientists to probe the laws of physics in the most intense gravitational fields known. But the galactic centre is more than a cluster of stars. It's a crucible of cosmic chemistry. Here, dense molecular clouds are bombarded by powerful X-rays, gamma rays and cosmic rays, creating a cocktail of exotic molecules and complex organic compounds. Unusual masers, natural cosmic lasers, shine in radio wavelengths, revealing the motion and makeup of the gas. Giant arches, filaments and bubbles of plasma are sculpted by the winds of massive stars and the explosive force of supernovae, forming intricate, ever-changing structures. Sagittarius A*, the supermassive black hole, is the heart of this chaos. Though it is currently quiet, feeding only sporadically on stray gas and dust, its past eruptions have left indelible marks. Enormous outflows and jets, visible in X-rays and radio waves, hint at ancient cosmic tantrums when the black hole blazed with the light of 1 billion suns. Even today, every so often, flares erupt from its vicinity, lighting up the surrounding clouds and sending ripples through space-time itself. The galactic centre is also a place of mystery. Strange radio signals, unidentified X-ray sources and even hints of dark matter interactions have all been detected here. Some scientists speculate that this region could be a prime site for the annihilation of dark matter particles, or even a haven for exotic objects like magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. To unravel these secrets, astronomers use an array of powerful telescopes, peering through the dust with infrared eyes, mapping the turbulence with radio waves, and capturing bursts of energy with X-ray and gamma-ray observatories. Each new discovery adds another piece to the puzzle, revealing a galactic centre that is far from quiet, a place of constant birth, death and transformation. In the end, the Milky Way's core is both a window into our galaxy's violent past and a key to its future. It is a reminder that even in the darkest places, the universe is alive with energy, motion, and the relentless drive to create and destroy. The galactic centre is the beating heart of the Milky Way, a heart whose rhythm shapes the destiny of every star, planet, and living thing in our cosmic home.